So let's visit acidification now in the context of something called calcite compensation depth, which turns out to be another important player in the carbon cycle. So we will look at quickly at pH again. So we have strong acids like hydrochloric acid, sulfuric acid, and nitric acid. Acids are basically that completely dissolve in water, so they would give you H plus and Cl minus in this case. So you have acidity measured essentially as the concentration of H plus. There is another concept called alkalinity in the ocean, which includes other things that we will not get into, but you can read up on it. Very important concept as well. So we defined pH as the log of concentration of H plus. So we already looked at this scale before. Pure water, distilled water is defined as neutral pH, which is 7. If the pH is less than that, like in rainwater, acid rain, volcanic lakes, lemon juice, vinegar, and so on, they are acidic. Ocean, we said, remains towards the basic or alkaline scale of this, towards 8.1, 8.2. So baking soda, bleach, desert lakes, and so on, seawater are greater than 7, just reminding ourselves. Why is it important for carbon cycle? It plays a role in weathering. So carbonic acid, remember CO2 is very soluble in water, so every time it rains and there is CO2 in the atmosphere, or there is CO2 on land and the river waters are bringing it in, there is carbonic acid which is going to weather all rocks, right? So this is a granite, which is actually much older than this limestone gravestones. So you can see that limestone weathers much easier than granite. Of course, there are also marbles, which is a metamorphized limestone, which is not as strong and corrosion resistant as granite. Granite is an igneous rock, limestone is a sedimentary rock, and so on and so forth. But this shows why we have to worry about pH again. We had already mentioned that this buffering ability of the ocean allows it to maintain its pH nearly constant and has done so for many million years. But when CO2 keeps increasing like we are doing in the industrial period, the equilibrium can shift. So this is showing where we are in terms of pH. We said we have already reduced it from the beginning of the Industrial Revolution because we have increased CO2 from 280 to 415. So this is the expected change. We will move in this direction. So the buffering ability tries to keep the pH constant by moving things around. So CO2 to HCO3 minus to CO3 minus minus occur in a ratio of 1 to 100 to 10. But you can see that as CO2 increases, carbonate ion drops off quickly. HCO3 reacts a little bit slowly, but it also eventually drops off. So you end up with reducing pH. This is our essential ocean acidification, right? So we can connect it to the carbon cycle by going back to chemical weathering, the limestone and the granite. What is the key there? So we will come back to this again. Calcium carbonate is interacting with carbonic acid, falling rain which is dissolving CO2, producing calcium ions which are going to wash into the ocean. Ocean has plenty of calcium ions. It's the carbonate ion that's critical for forming calcium carbonate shells. And bicarbonate. So CaCO3 plus H2CO3 is going to give you calcium ions and bicarbonate ions. When we will see later on that the carbonate shell formation equation goes exactly the opposite, which means when calcium carbonate is formed, you form H2CO3 again, which is essentially CO2 because this is just dissolved CO2. So calcium carbonate is going to be releasing that CO2 back. Whereas silicate weathering, rocks like wollastonite, which is calcium, silica, and oxygen. I don't even know what the chemical name is, but you can look it up. Combines with 2 molecules of H2CO3. I hope you're all familiar with the concept of moles. Typically we talk about 1 mole of wollastonite interacting with 2 moles of carbonic acid, producing 1 mole of calcium ion, 2 bicarbonate, silica, and water. This silica is used up by diatoms and other silica shell forming animals. And mole is what? Essentially it's the number of molecules in 1 molecular weight of 1 gram of carbon dioxide, which is 1 molecular weight of carbon dioxide, which is 12 grams. So that is the Avogadro number, 6.02 10 to the 23. Okay, so since the mass number or the molecular weight of different things are different, it's easier to deal with moles. Mole is just like a dozen. You say dozen is 12, right? If you do it in mass, it becomes very complicated. But if you just say 1 mole, 1 mole, 1 mole, 1 mole of any substance has 6.02 10 to the 23 atoms or molecules. Okay, look it up in case I screwed it up a little bit. Okay, so main point is silicate weathering takes up 2 CO2 molecules. You can think of H2CO3 as essentially dissolved CO2. So it takes up 2 CO2. Even if one is released back, you are hiding away 1 CO2 molecules with silicate weathering. So silicate weathering sequesters 1 carbon molecule. So in the long term, you have to bring it back. So you need a feedback. We'll look at that later on. So calcium carbonate deposition becomes important in this case. So if calcium carbonate shells are forming near the surface and they die and drop, remember CO2 increases with depth, which means ocean waters are acidic with depth, and calcium carbonate dissolves with carbonic acid. Okay, so this is calcium carbonate forming, but when calcium carbonate drops to the ocean, H2CO3 is going to increase, so it's going to release calcium and form bicarbonate, right? So when does calcium carbonate get deposited and then convert to limestone or marble or whatever, right? Essentially, if you think about acidification with depth, natural increase in CO2, if the dissolution of the calcium carbonate stops at some point and then it can sink to the bottom, then it will get deposited, right? That can happen when there is very shallow water column along the mid-ocean ridge, for example, here, and the ridges over here and here. Okay, these are the ridges. Okay, these are the areas with more than 75% calcium carbonate. Why is that? Basically, calcium carbonate is raining down and carbonic acid is trying to dissolve it, and a point where the rain rate and the dissolution rates are the same, then there is no dissolution below that. So if the shell gets past that point, then it will reach the bottom and get buried. It may get mineralized at the bottom by microbes, but nonetheless, that depth where the rain rate of calcium carbonate and the dissolution rate are the same is called calcium carbonate calcite deposition, calcite compensation depth, CCD, calcite compensation depth. That's where calcium carbonate will get deposited. So these are the shallow depths where calcium carbonate falls and then it hits the bottom. Of course, there are details because once it falls on the mid-ocean ridge, slowly it can slide down to deeper depths and get dissolved again because it's getting into more acidic waters as well. But nonetheless, there is high concentration of calcium carbonate below the CCD, calcite compensation depth. Calcite compensation depth. Remember, okay, listen to the podcast again. Forget my screw up and listen to calcite compensation depth is where rain rate of calcium carbonate is the same as the dissolution. I realized based on a message from Tuba Khan on my channel that I had screwed up this podcast on calcite compensation depth. This was the first course I did, in fact, during COVID, because I was stuck and was getting bored. But anyway, I enjoy doing these, but sometimes you make mistakes, sometimes you make very silly mistakes. So calcite compensation depth is the depth at which the rain rate of calcium carbonate from the top, could be in the form of calcite or aragonite, is dissolving at the same rate that it is coming down. So there is aragonite, which is more unstable, so you have aragonite compensation depth, which is a few kilometers shallower than the calcite compensation depth, because calcite dissolves at a deeper depth where temperatures are lower, pressure is higher, saturation levels are lower, and or it's not saturated, so the dissolution rate goes up. So there is the lysocline where the saturation ends, and then the dissolution of they are also called solvation and hydration, so I won't go into the details, but below the lysocline, the dissolution of calcium carbonate in general, or aragonite and calcite, begin to increase, and the depth at which the rain rate and the dissolution rate are the same for calcite is called the calcite compensation depth. And for the deposition of calcium carbonate to happen, actually the bottom has to be above this depth, because below the calcium compensation depth there will be complete dissolution of the it's all dissolved by the time you reach CCD. So I said it completely wrong. Thank you, Tuba, for pointing it out. So I'm going to add this clip at the end. It's been watched already a few times, so hopefully the people that follow will not learn the wrong thing from me. Sometimes when you do these things you are not being careful enough, so apologies, but remember that calcite compensation depth is where dissolution is complete in terms of any amount that is coming down from the top. So if deposition has to happen, then the CCD, calcite deposition depth, has to be deeper than the bottom topography. So that's what happens at these mid-ocean ridges and so on, where it's very shallow, so it's above the CCD or calcite compensation depth, but once it's deposited it can slide down the bottom and stay below the CCD or stay at the bottom and keep undissolved, let's say, and you can find deposits of calcite at deeper depths, basically because they got deposited above the CCD and slid down the bottom slopes and so on and so forth. Subtle point, important point, very important point, so sorry for screwing that up. Okay, hopefully this addition will help.